Yes, I'm going to talk about briefly the geotechnical application of SPH. The work was mainly done by PhD students. Um, so the first application I'm going to talk is about the rapid landslides. And traditionally, people use finite element method to simulate the initiation and the progress, the subsequent landslide phenomenon, but it has problem with the distortion of the grid because of the large deformation. The governing equations are the weakly compressible Navier-Stokes type equations, but in modeling soil movement, we replace the fluid stress by different soil constitutive models. So here, the shear stress is related to the internal friction angle of soil and the effective stress. So basically the normal stress between soil grains. But in our simulations, we use incompressible SPH. So the standard projection method is used. And between the predictor and corrector steps, we solve the Poisson equation to guarantee the divergence of the flow field is 0. This is the collapse of a very slender soil column. So as can be seen that only this wedge undergoes significant movement, while the central triangular part of the column doesn't move much, which is as predicted by the theory. And for shallow soil column, only the right bit of the soil moves. And we also compared our simulations with the experimental results. And the next application of the SPH simulation in the context of landslides is to do the parametric studies to find out how the runout distance is related to different properties of the landslide. So this is the idealized setup of the simulation. So the initial soil is confined in this rectangle with length L0, height H0, and the final shape of the deposition has length L infinity, and the overall distance between the initial front of the soil column and the final front of the soil column is L reach, which is an indication of the runout. And again, we compared our simulation, so final shape of the deposition with the experimental results, which show good agreement. So this is when we change the slope to be 70 degree. The final shape of the soil column is well predicted. So the biggest conclusion, the most important conclusion after the parametric studies is that the non-dimensional runout distance, when normalized by the square root of the area of the soil column, on the angle of the slope, the height of the drop, and also the internal friction angle, the initial shape of the landslide mass does not matter much. And so the so this final the bottom right figure shows the relationship between the normalized runout distance and the normalized drop height. So for all the slope angles, the relationship is not linear. When the drop height, non-dimensional drop height, is sufficiently large, the non-dimensional runout distance approaches a constant value. So the implication is when the landslide mass increases, which means the non-dimensional drop height is decreased towards the origin, then the ratio between L infinity and HD increases. But the reach angle, theta reach, is actually related to HD over L infinity. So as the volume of the landslide increases, this angle should decrease. And this trend is inconsistent with the observations of the real landslide phenomenon. So as the landslide mass increases, statistics show that the reach angle indeed decreases. We also run simulations to calculate the impact force and overturning moment of the retaining wall during the landslide. So in order to prevent particles escaping from the domain, we add this L-shaped wall, but only the force on this short downstream wall is computed. So as you can see, the soil particles are almost stagnant in a triangular zone in front of the retaining wall, but above this stagnation region, there is very rapid soil particle movement. And we calculate the impact force variation with time, and also the overturning moment variation with time. So the main conclusion is that the force on the retaining wall can be regarded to be composed of two components. One is the hydrostatic part corresponding to this triangular stagnation zone. The other is the hydrodynamic part corresponding to the rapid movement of the soil columns overlying this stagnation region. And the addition of these two parts give you the overall impact force. And from such distribution of the impact stress or pressure, we can calculate the overturning moment as well. We have also used the SPH model to simulate a real landslide phenomenon in Hong Kong. So the initial profile of the ground is this dashed line. In Hong Kong and other mountainous cities, in order to create more flattened area for property development, people make cut slopes. So basically they steepen a part of the slope to create some area to develop for property development. But during heavy rainfall, the landslide is a big problem. So this is a simulation of the landslide processes. The main trigger for the landslide is the groundwater flow. So during the heavy rainfall, the water table increases in the soil, reducing the effective stress causing the landslide. So in our simulations, we assume the soil movement is entirely undrained. So the influence of the pore pressure can be approximated by a reduced internal friction angle, so corresponding to different pore pressure at different locations in the column. So there are different internal friction angles. And during movement, we assume the dissipation of the pore pressure is not significant. So the friction angle for a group of soil particles remain constant during the movement. The next topic I want to mention is the solitary wave interaction with permeable beaches. So traditionally, people often assume that the beach is solid, impermeable, and there have been a lot of analytical study and also experiments to study how the run-up height on the beach is related to the slope and also the height of the incoming waves. And this is a solution to the Busnesq equation to calculate the amplification of the wave height during the run-up. And so this is the results of our simulations almost 10 years ago. So assuming this is the beach surface is basically a solid boundary, then using the depth averaged shallow water equations or Busnesq equations or particle-based methods to predict the wave evolution and also the maximum run-up height versus the incoming wave height. And at this point, wave breaking occurs, so the run-up height increase slows down. The governing equations for the flow inside and outside the porous media or the permeable beach are like this. So here U is basically simply the flow velocity in the pure fluid region, but inside the porous media, it is the Darcy equivalent velocity. And the extra resistance force R represents the drag force imposed by the soil skeleton on the water inside the porous media, but in the pure fluid region, R is simply equal to 0. And the value of R is given by this Ergun law, where Kp is the permeability and Nw represents the porosity. And these two values are related to the grain size of the beach. So again, we use the incompressible SPH simulation. In this application, the pressure Poisson equation the source term of the partial Poisson equation is a combination of this divergence-free formulation and the truly the constant density formulation. An important numerical technique we have to use in this application is to change the density of the fluid particle when the smoothing particle goes in and out of the porous medium. And correspondingly, the volume of the particle should also change. So inside, in the middle of the porous media, the apparent density is equal to porosity times the density of water, which is 1,000 kilogram per cubic meter. Correspondingly, the volume of particle increases inside the porous medium. At the interface, there is a transition zone. So the density gradually decreases from 1,000 to about 500. So 1,000 in the pure fluid region to about 500 in the porous medium, depending on the value of the porosity. So the consistency condition in SPH is still maintained inside the porous medium as the particle becomes sparser, but the volume become increased. And so there should also be some caution about the judgment of the surface particles for solving the Poisson equation. So in the pure fluid region, it's very straightforward. So we just choose a threshold value, and when the calculated density is less than this ratio times 1,000, then this particle is regarded as the water, as the surface particle. But inside the porous medium, well, we need to calculate a reference density using the porous particles in the same algorithm as for the for calculating the density of the smoothing particles in that location. And then when the ratio of the water particle inside the porous medium over the reference density is less than the threshold value, then the particle in the porous medium is regarded as the water surface particle. So here is one verification case. The water column collapses and impacts on the porous block to the right. So as you can see, the initial setup, so this is the initial water column on the left, and inside the porous block, the density of the water particles is smaller, and on the right is pure fluid again. So this is the water surface profile at 0.4 seconds after the collapse, and so on. The second verification is the wave run-up, solitary wave run-up on a solid slope. So the solitary wave is generated by moving the piston on the left, and then we compared the run-up height with various analytical results and also the experimental results. So here, the application is the run-up of the incoming solitary wave on a porous triangular permeable beach with different grain size. So this is when the grain size is very small, the beach is almost impermeable, behaving in a similar way to the solid beach. So as the time progresses, there is very little variation, movement of the water particles inside the beach. But when the diameter increases to 1 millimeter, you can see clearly there are, so as the wave running up, so there are some changes in the velocity and also the pressure in the water table inside the beach. So this is the relationship between the run-up height with the mean grain size inside the beach, corresponding to 2 incident wave heights. So in this logarithmic plots, so for both wave heights, so the run-up height almost linearly decrease with the grain size. And then we proposed an empirical equation to predict the run-up height according to the grain size in the beach, using the run-up height on a solid beach of the same slope with the same incoming wave height as the reference, which is RS here. So to summarize, so we have used incompressible SPH methods to calculate very rapid landslide phenomena, and also the solitary wave run-up on the permeable beach. For the landslide application, we use various soil constitutive models, including Mohr-Coulomb model, and also the strain rate dependent model, etc. And we proposed some empirical relationship between the runout distance and the reach angle, which is the angle of the final runout of the final position of the mass and the initial position of the landslide mass. For the simulation of the wave interaction with porous medium, we introduced the apparent density and apparent volume concept, so that consistency is still guaranteed when particles are more sparsely distributed inside the porous medium. And we also established some empirical law to predict the maximum run-up height over a permeable triangular beach. So that's all. Thank you.
Thank you very much, Dongfang.
Stop sharing. Yeah.
Yeah. So we've got a couple of questions that are coming through the Q&A. So the first is from an anonymous attendee, very mysterious, but it says, "Good afternoon, Yang." Dongfang, I assume. One question: do you take into account the temperature of your system?
The temperature of I suppose it's the temperature of water. No, we assume temperature is constant, 15 degrees C. So the viscosity and density of water, which are important for deciding the drag force between the water particles and soil skeleton, So they are not changed during the simulation.
Okay, thank you. So actually reading the second question, it's from Jonathan. I think perhaps Jonathan was the anonymous attendee, because the next question is, in the equations, you couldn't see the variable of the temperature. I think the second question actually is a follow-on from the first. Okay, are there any further questions from the panel? Anything else on the Q&A at the moment? Open questions? Okay, no further questions. Okay, so I'm sort of quite conscious that we should be having a bit of a break at the moment. I was just wondering if you're aware of the work that's gone on at Manchester. So George Fotakis, who I think is attending, he can't speak. So I apologize, George, when I misrepresent what you've done in the past, but I think he's done sort of kind of a multi-phase implementation using the dualist physics software. And I mean, I don't know exactly if the applications are the same, but I was wondering, are you aware of that work?
Not really. I'll take a look afterwards.
Okay. I could be suggesting something that's completely different. Oh, Ben has his hand up. I suppose Ben could probably be George's voice in this regard.
It's slightly different what Dongfang's doing to what George was doing. George was doing sort of sediment transport, and so actually the movement of sediment off a bed, whereas Dongfang's doing more sort of permeable flow. But some of Dongfang's initial stuff was looking at dry granular flows. Yeah. So I think George's work is between what Dongfang is doing, slightly different.
Okay.
Yeah. I'll take a look anyway. Thank you.
Okay. Right. So in the schedule we have now until